Right. Well, welcome everybody to the last session in this room for DataWorks 18. Thanks for sticking with me. My name is Tom Phelan. I'm the chief architect at a company known as BlueData. Today I'll be speaking about some lessons we've learned when running Spark on Docker containers. Before we start, I'd like to get an idea of your familiarity with the subject matter. So how many people are familiar with Spark or have used Spark today? Good number. How about Docker? How many people are familiar with Docker containers? Good. Now how about the trick question? How many have ever used BlueData before? Wow, good, fantastic, 2 people. I'm in a family of friends here. So BlueData is a startup. Well, we've been like 5 or 6 years in business now. And what we do is we deploy a virtualized platform that allow data scientists to have a self-service environment for deploying any sort of big data distributed cluster on a containerized system. Through that, we have worked with many enterprises all over the world, making sure that when we deploy their big data applications, in this case big data clusters, into their environment, that it works well. It works right every time. Security is maintained. Data access is maintained, and performance is maintained. So what I'll be talking about today are some of the lessons that we have learned during this odyssey of getting Spark to run in a virtualized environment in the enterprise. So we'll be covering a couple of topics. Since not everybody is an expert on Docker containers, I'll do a very slight review of what they are and why they're valuable. We'll talk a little bit about big data and then the challenges of deploying Spark on Docker, then go into the meat of the presentation, the lessons that we learned, and then some key takeaways and perhaps some time for Q&A at the very end. So let's begin. To look at Spark models, there's 3 major deployment models for Spark. Most common for the individual data scientist is just to take the Spark software itself, deploy it on a laptop. This is where you run the Spark master and the Spark worker on the same physical host. It's very easy to do. The data scientist can then go ahead and use Python or R or any of their familiar languages to go ahead and submit jobs to the Spark distributed processing service. And away you go. And basically this is where you get the famous statement from the data scientist, well, it works on my laptop. Okay, it may not work on yours, but it works on mine because I control everything on my laptop. Moving forward to the next set of complex deployments is an on-premise cluster. This is what you most normally would see in an enterprise environment. There would be a sequence, anywhere between 5 to 10 to several dozen to several hundred different physical hosts running the Spark distributed processing system, and then running all the data or the processing in parallel to get the results of the queries. And finally, what is becoming more and more popular is deploying Spark in a public cloud. We won't address that so much today. Today I'll be speaking mostly about that second deployment model, which is deploying Spark in an enterprise on a large number of physical hosts so that real live computation and querying can be done on Spark. When we deploy a Spark cluster in the enterprise, what becomes clearly visible is that there are 2 competing interests within the enterprise. The first interest is obviously the data scientist. And when I say data scientist, I kind of mean it in a generalized term. It's not just the data scientists, it's also the data curator, the coordinator, the person who collects the data, who manages it, cleans it, all that I kind of lump under the data scientist. What that group of individuals is most interested in is running the latest tool sets on their cluster. They want to go to the Apache source code for Spark, download the latest version. They want to use the latest notebooks from Zeppelin or Jupyter. They want to use all the latest RStudio, Sparkle R, Python, whatever they want to use. They want to use it all fast, have it working now, and they want to use it against real data. They don't want sample data sets or old data sets. They want to make sure that when they move their algorithm out of deployment and into the production tier, that it actually works correctly. So they need real data to do that. However, on the other side of the coin are the IT personnel. These are the people that are responsible for the security of the organization at the enterprise. They are in charge of making sure that only the right people get access to the right data. They have to be worried about things like network isolation, data integrity, and multi-tenancy if there are multiple organizations within the single enterprise who have competing needs for various quality of service on shared physical hardware and access to shared data sets. So what we have here is two different groups of people which we need to satisfy in order to deploy Spark in a virtualized environment in the enterprise. One is all about flexibility, one is all about control. And I'll talk about how we address both those items going forward. Now a bit about Docker containers. They also have the concept of flexibility and control. Let's talk about the application side first. Docker containers is when we say Docker containers, we typically refer to two components. We refer to a ASCII text file, which contains a description of the software which will eventually be run in the container. Okay, that's a static description. Then we also talk about the runtime, the container itself, which is a unit of scheduling and resource isolation on the Linux host. I'm talking about both those items together when I refer to this slide. On the right-hand side, the application, what I'm referring to here is with the foolproof packaging, is when you specify or you write into a Docker specification file, you say, I want this version of Linux. It might be CentOS 7.3 or whatever it is with some set of patches. I want to use this version of Spark. It might be Apache 2.3 or something else. And I want to use these various pieces of software which complement my Spark cluster. And I want to be able to reproduce this quickly. I want one person to spend the time to figure out how to specify the software stack, and then I want all my other data scientists to be able to benefit from that stack of software so they don't have to go through the whole concept of patching and upgrading and configuring. I want to be able to reproduce the deployment model of this application or this entire software stack very quickly. And I want to do it with no performance penalty, obviously. It has to be fast, it has to be cheap, and it has to work right. That's the whole power of doing a repeatable, deployable process in the enterprise. And that's what we get from the infrastructure side. Not only once we specify the software stack, with the power of containers, that software stack can then be deployed not only on a physical host in your data center, it can be deployed on a public cloud, it can be deployed in different clusters with different rates of service, quality of service. So what we typically see is when we go into an enterprise, the enterprise will have some number of servers called 100 servers just for a round number. They are running dozens of different clusters on that 100 physical hosts, and those clusters are in different tiers. Some are sandbox or development environments, some are test or QA environments, and finally some are production environments. Each one of those tiers has different requirements around quality of service and data reliability. Any system that you want to put together, you want to build, has to be able to handle that flexibility. Obviously, higher efficient resource utilization is the key. You don't want to do this if you're going to increase costs for the enterprise. You only want to do it if you can reduce the costs. Okay, so that's why Docker containers are our friends. And this almost goes without saying, but I thought I'd say it anyway, is the experience that we learned here is not only applicable to the Spark application or Spark distributed processing framework, but any open source big data solution. With the Epic platform, which is the platform that BlueData works on, it will support any open source solution. And so the information I'll be talking about today, while targeted at Spark, is easily extendable to any application, whether it's Hadoop, Cassandra, TensorFlow, it can even be Splunk or any other application like that. Now, how many people, by a show of hands, attended this morning's presentation on Spark on Kubernetes? Okay, a few people, good. I just wanted to bring this out first because we're not opinionated about the container orchestrator. The material that I'll be talking about today can be applied to any container orchestrator. What I'm really going to walk you through in the next slides is, hey, you are set up, you're architecting, you're trying to develop for your enterprise a system that will allow the creation and management of big data clusters in a virtualized environment. These are the questions I'm going to be raising and some of the answers that we've talked about. If we take a look at Apache Spark 2.3, there are currently 4 different methodologies for scheduling the executors for the individual Spark cluster. You could use Spark standalone, which means it has its own built-in scheduler, Spark on Yarn, Spark on Mesos, and finally what's just released in 2.3 is a version where the Spark executors can be integrated with a Kubernetes cluster, and you can use the Kubernetes orchestrator from there. Like I say, I'm not making a specification on one or the other, but what I'm talking about, and it'll become clear, is that we're talking about a different level of deployment model. We're not talking specifically about the scheduling of the executor processes within the individual Spark cluster. We're talking about running the entire Spark cluster and multiple Spark clusters in a virtualized environment. Okay. So let's just begin. So we start out with a clear goal in sight. We are at an enterprise. We want to be able to offer our internal data scientists the ability to run any big data application. We'll focus on Spark today on a virtualized environment, so they don't have to worry about version control. They don't have to worry about security upgrades, but they still get to use all the tools that they want. So that's our goal. And we're going to start out with this toolbox. Okay, this thing called Docker sounds pretty good. Let's use it to deploy our applications. Just as a caveat, I came from 10 years at VMware, so I know all about VMs, and we still selected the Docker container as the deployment solution for big data because we didn't think that the overhead of virtual machines was required for this solution. Okay. And so let's talk about the pitfalls and challenges that occurred along the way. First of all, we have to look at these container managers, and there are a number of container managers available in the open source environment. Kubernetes, OpenShift if you're looking at a Red Hat environment, DCOS if you're familiar with Mesosphere and Mesos deployment, even Docker Swarm. What I would suggest though is as we look at, you have to determine, I wouldn't focus on the technology first, I would focus on what are your needs. Each of these container orchestrators has different value propositions, and so what you need to understand first is what do you need from the container orchestrator. Some of these container orchestrators are more complex than others. Perhaps they have a richer feature set. Other ones are designed for, or originally designed for, stateless applications as opposed to stateful applications, and we'll talk a little bit about that more as we go forward, and so forth. And what I would also say is people often ask me, well, hey, what orchestrator would you suggest we use? Hey, and if I look back on the experience that we have had over the last 5 or 6 years of doing this, I would probably have said 24 months ago that I would have gone with something like Docker Swarm, okay, because neither Mesos nor Kubernetes at that time were mature. And then if you asked me now 12 months ago, I would have probably said Mesosphere. That looked like it was pretty good, had a lot of traction. Today, I'd say both of those are lost, and I'd say Kubernetes is the way to go today. So when you ask that question, you have to understand what technology is available today, what technology might be available in the future. And so when you select technology, make sure it fits your need rather than the other way around, trying to fit your need to a given technology. Then, of course, you have storage configurations, and we'll talk about this a little more as we go forward. But since we are talking about big data, you always have to understand where your data is coming from. Does it reside in an existing data lake? Do you have, we go into customers who have 10 years worth of data stored in an HDFS data lake. How will you access that data quickly? Maybe they're using Ceph, a newer kind of version file system. Maybe they're using object storage, perhaps from S3 or from somewhere else. Then we have network configurations. This is probably the biggest stumbling block that we see. When we go into an enterprise, there are always network considerations. Security, and so forth. And this is where you'll really have to do your homework up front when you're designing your system. You need to understand what your network requirements are. So I could say, yeah, Docker networking is great. Kubernetes, obviously, a pluggable architecture, very flexible. Flannel, Weave, all the other ones, Calico, excellent solutions. But what you have to understand is, more importantly, do you need IP persistence with your container? Do you expect your container to go up and down? Do you expect your container to be migrated from one physical host to another? And do you expect the IP address to be persisted? That depends on what experience you wish to give to your data scientist, what applications you're running in your system. And we'll go into more detail on this, but it also requires, hey, will your data scientist be accessing your Spark cluster via a command line and use the CLI, or will they be accessing it only as a web service using a notebook such as Zeppelin or Jupyter? Once you determine the workflow that you wish to support, it will put requirements on your network architecture, and from there you can then select a network implementation to overlay on top of your physical network. That will then give you the privacy, the security, and the flexibility that you need. One thing that we have run into in the enterprise is we're talking about running thousands of nodes of Spark. When I say a node, I mean a unit of Spark deployment, so it's a container. So that means you have thousands, if not tens of thousands, of IP addresses that you need to come up with, right? Most enterprises don't have that kind of region within their addressable IP space in order to deploy, even for a big data application framework. So that's where you need to choose private IPs versus, when I mean private, I mean non-routable IP addresses versus routable IP addresses within the enterprise. Now there's trade-offs on both. Obviously, if you select private IPs, then there's no upper bound on the number of units of Spark processing you can have. However, you will have to have some sort of proxy-ish type of thing in front of that private IP address so that the data scientist sitting at their desk using their Macintosh or their PC can actually connect to the processing unit for Spark. They can only connect to publicly addressable IP address nodes, so you need a mapping between that public address and the private IP address that's associated with your individual cluster. Okay. Obviously, we're talking about performance. This is big data, and you can have all the flexibility, all the agility in the world, and if you can't have reasonable performance, no one's going to be able to use it, even if it's cheaper and better. So we'll talk about how we can maintain the performance. One of the big questions, which is frequently overlooked, especially in kind of do-it-yourself deployment models at an enterprise, is most of the work comes at the back end, comes after you get your first cluster up and deployed in your virtualized environment. It's fairly straightforward to take one version of Apache, Spark, a fixed collection of software solutions on top of that, get it running in a container. But then what do you do? How do you update the individual software pieces? And we're talking about not only the software components within the Spark cluster, but also the security patches, which inevitably have to be placed on the physical host operating systems themselves. So how that's managed is really tricky, and that's why they say, when you get 80% of your deployment completed, that last 20% takes another 80% of your time in order to get the details done. Once again, these are all the stack of software that we spoke about earlier. And then there's failures, right? Everybody has mistakes. You may not have correctly identified your stakeholders within the enterprise. You may not have correctly identified all the use cases that were required. And remember, a do-it-yourself product is only cheap if you get it right the first time. If you have to do the product 2 or 3 or 4 times, then whatever value you had by doing it internally has been lost. So you want to make sure you control mistakes. Okay. One of the ones that we found most interesting over the years, and this is something that's probably happened in the last 18 months, is that when we would go to an enterprise, they would say, we would ask them, what the future is for big data in their environment. They'd say, okay, we are dedicated to running everything on premise. We have not yet worked out the security models for running our big data analysis in the public cloud. We have to have all our data on-prem. That's what those are the systems that we rolled out for them, 18 months ago. But if you talk to any person today, any CIO of a major company, and the person in charge of the CDO, the Chief Data Officer, they've all worked this out. So here we are, 18 months. Everybody has a cloud-first initiative. They may, in fact, have hardware and some data residing on-premise, but they're all within a multi-year plan to move all of that into a public cloud. So what you want to do is when you lay out the future, make sure you take this into account. You'll always be using some sort of hybrid model where you need to combine on-premise resources and data with public cloud resources and data. And now you've done all this, maybe you've gotten to the top. But now remember, we're talking about an enterprise system here. So you still have to worry about high availability. You can't have any single points of failure. You can't have any downtime. How do you handle, or are you going to handle data backup and recovery, multi-container upgrades and patches, all these things which only come out once you have to go through the security audit or the uptime audit within an enterprise. So these are things you want to lay down in your design when you first talk about it. Okay, this is where you might get some help, and that's why you're coming to the presentation today. So what we have done, what BlueData has had in the last 5 years, just to recap, is to take a solution like Docker containers and these multi-service big data applications and get them to run together, and we do it with a performance of bare metal, so there's no performance loss. So let's just talk about some of the things that we had to do. Before we even wrote one line of code, we wanted to put down on paper some design decisions so that we knew when we put together our deployment that we actually met what our goals were. Our first goal was to run unmodified big data software. So if you talk to other organizations, they're trying to move what is essentially a legacy monolithic application. Though we don't like to say it, Spark and Hadoop itself is at least 15 years old, right? It was developed back in the mid-2000s, okay? It wasn't cloud structured. They are big collections of cooperating services that are heavily stateful, okay? And what we're trying to do is bring a deployment model which is designed for stateless applications and a microservices cloud-based architecture, trying to bring those monolithic solutions and deploy them on this architecture. But what we wanted to do is, rather than requiring any change to the open source software, we wanted to take it as it is and deploy it in a containerized environment. To that end, what we did is we deployed all the services that would typically be running in a given Spark role node in the same container. So they would be all scheduled the same, they would be bound together in a single unit, and they would be able to cooperate without having to go across a network. When I say a Spark role node, what I mean by that is when you deploy a Spark cluster, you have at least 3 different types of nodes. You will have the Spark master or Spark controller, which is the controlling framework itself. You will have a collection of 1 or more Spark worker nodes, which is where the executors are actually run. And then you'll have 1 or more roles called edge nodes. And these edge nodes run services that are ancillary but complementary to the Spark processing cluster itself. So there'll be the services such as your Zeppelin or Jupyter notebooks and whatever else you have to, or if you're running some sort of input feeds or something like that. So what we wanted to do is make sure that on our deployment, so on our virtual environment, when a data scientist runs there or gets an application, a Spark cluster deployed on our environment, they have exactly the same experience that they would have on their bare metal solution. They've been using Spark for many years. They've been using Hadoop for many years. They have their own ways of interacting with the platform or with the application. We want to make sure they can access and manipulate the platform in exactly the same way. One of the other key design points is that we're talking about multi-tenancy, storage and networking, and user management and access control. These are first principles. what we're not talking about is a university example where we cobbled together some open source software. We're talking about software that's being used at an enterprise where security, authentication, and reliability have to be built up and they have to work right the first time. Okay. Other things that we talked about, or that were our design decisions when we first laid out our architecture, is we had this concept of auto configuration. Now, on the last slide, I just got through telling you that there are multiple roles for nodes of an individual Spark cluster. So there will be a controller node, master node, with some set of services, workers, and then edge nodes. At first, you might say, hey, I will specify a Docker image file or container file for each of my different role types. That way I can minimize the amount of software that I'm installing in that container. It will come up more quickly. It will be easier to use. Well, in fact, after we played with this for a while, what we found is that perhaps was the common solution was probably not the best solution. What we did is we created a single Docker file that at instantiation time could automatically morph itself or configure itself into any one of the node types required or roles for that particular cluster. What this allowed us to do is when we modified one version of a version of the software in one of the nodes, it automatically was deployed or changed in all the other nodes of the cluster. This way, we greatly reduced our QA matrix when we had to update the software, the individual pieces of the software within the container. They were all guaranteed to work no matter what role node they were in. That's why we deploy a single Docker file, single Docker specification. It is heavier weight, no doubt about it. We use the squash command to squish it down as small as possible. It is larger because it contains all the software, and some of that software may not even be run in that particular role node for that particular node of Docker cluster. But in the end, it benefited us because it reduced our maintenance cycle as we went forward with the clusters. Now, the whole point of Docker containers is that containers are lightweight, right? We wanted to maintain that lightweight, flexible, high-performance virtualization abstraction. Otherwise, we would have gone to VMs. So what we did is we separated the compute resources from the persistent storage resources. Now, I know that's a topic for another presentation, but that is what we talked. There's reasons for that, but if you talked even 5 years ago, 6 years ago, everyone would have said that was heresy. The only way you can get high performance is to co-locate compute and storage. If you maintained that belief set or that architecture, virtualization would become next to impossible. So technology has improved. We've moved along. It is now no longer necessary to bring the compute to the storage in order to get high performance with big data applications. So what we've taken advantage of that now is we've isolated the compute to the containerized environment. The storage resides externally. But there is this magic stuff. There's like container storage. Now, what is that? When you instantiate a container, there is at least a small portion of storage, persistent storage, associated with that container. That container, that storage, is where the configuration information for that particular container is. That needs to be persisted. That still needs to work. The reason you need that is because, as I spoke about earlier, what we're really doing here is we're trying to bring a monolithic stateful application into a containerized stateless environment. One of the trade-offs is to have this little bit of container storage in order to store that ephemeral data. The key is, though, that it's ephemeral. Data is not persisted there beyond the life cycle or the lifespan of the individual container. Okay. Resource utilization. What we found is when working with data scientists, they were much more comfortable thinking of compute resources as virtual CPUs or virtual cores. Nobody understood what a share meant. What's a share? I mean, so you have these containers which have CPU shares. What we did is we provided an overlay system so that resources could be specified to a container based on virtual CPU count. Another lesson we learned is you can do over-provisioning. You can do over-provisioning with containers on both CPU and memory resources. Kind of on a case-by-case basis, we would permit a customer or a user to over-provision CPU. It's a little bit dangerous because if you end up in a situation where you have stored too many running containers on a given host and they all decide to be active at one time at max utilization, you could get a case where one container would impact the performance of another container, and that's not something what you want. You can control it a little bit with the CPU shares and kind of sharing, but it's still a situation you want to avoid. We strictly did not and do not recommend over-provisioning of memory. Once you start to swap on a physical server, all performance that's running in the containers, it goes out the window. So I'd be very leery of over-provisioning of memory. I spoke a little bit about the networking to begin with. It's key in the BlueData solution. We just selected Open vSwitch, OVS, as our overlay network technology, mostly because it was the most flexible and it was orchestration, container orchestration independent. What we do is we create a VLAN or a VXLAN per tenant. For the multi-tenancy solution, what we wanted to do is make it as isolated as possible. So users are members of one or more tenants. Tenant is the unit of security. So with a tenant, any clusters that are stood up on behalf of a user of that tenant share the same VXLAN running on the physical hosts. They also share data isolation or rules, but that's a different issue. And so what this gives us is a guarantee that even though you have multiple containers owned by different tenants running on the same physical host, there's no possibility of even a malignant user who gets access to one container from accessing or snooping the network traffic of a container belonging to another tenant. This was key to being able to pass network security audits within the enterprise. Okay, this is just a simple example. What I'm showing here, the two, in this case, rectangular grayish boxes are physical hosts. There is a single NIC network card between in each physical host, a full mesh of VXLAN tunnels. In this case, what I'm showing is just two tenants. One is the red tenant at the top, showing the network connectivity between multiple containers on one physical host and a container on another physical host, and at the same time a second container on that same host connected to an isolated tenant network, so there's no chance of network traffic snooping. Okay, with storage, as I spoke earlier about that storage, I'd love to talk about. I'm a storage geek, but that's not the talk that I'm talking about today. Is we've separated compute and storage. We have our own technology which accelerates and reduces the latency of moving data from a remote data lake into a container. So that's how we get past the network hiccups that could possibly occur. Just a specification about the container storage, which I briefly alluded to earlier. What we would select, and this is probably obvious to most people, is to grab all the physical disk drives, and this can be SSD drives as well, on the physical host, place them into a logical volume on top of Linux. Past that, we use a thin provision pool to the Docker scheduler on Linux, and then allow the Docker scheduler itself to allocate logical volumes from that pool and associate it with the running containers. That allows you to get striped parallelism using all the physical spindles on the individual host to get the maximum performance for whatever ephemeral storage disk storage you need in a container. Key here is we found that enterprises want to store all their Docker images in a single repository that they control. Okay, we had initially had a number of solutions where we cached Docker images locally in order to avoid having to draw a Docker image from a centralized repository and place it on a physical cluster before we instantiated it. We found that that really didn't sit well with most enterprises because they wanted to have the ability for each user to check in and check out a Docker image and to be able to run security scans on any of the code that was checked into the Docker registry. So I would highly recommend you take advantage of that in your deployments. With Docker containers themselves, and this is getting a little low level, but we run the containers as non-privileged. So when you run a Docker container on a host, it can be marked as running privileged, means it has root access, or it can be run as non-privileged. Now, over the last 3 or 4 years, the security of the Docker container has been greatly improved. There used to be a pretty big attack plane where software running within a container could harm the underlying OS or harm other containers running on the physical host. That attack plane is greatly confined if you run non-privileged containers. So you just assign them the only privileges they have. And so what we did is we carefully looked at all the what are called capabilities for a container, and then when we launch a container, we turn on or allow only the minimal set of capabilities that actually allow the Spark software to be configured and run. So take very careful note of this. When you are running Spark or a big data Hadoop application in a container, you want to carefully control the capabilities so that you don't inadvertently introduce a security exploit. Okay, this is, I'm sure you've seen these before, but this is just a sample example of a Docker file where we specify the version of the OS, the software that is running. In this case, we happen to be running just an older version of 201 Spark with the Zeppelin, and then this configuration information is the invocation of some scripts which allow the auto configuration of this cluster or of this Docker specification into the various node roles when the cluster is instantiated at runtime. To look again at kind of think about this a different way, there are the software components, and that's what the top 3 lines of that Dockerfile, and then there is some application configuration information, which are the lower 3 or the lower 2 lines of that file. To think of this another way is these Docker container specifications are more like templates. Okay, so they are a proto cluster. When the cluster is brought up at runtime, then the template information is populated. And that's what the BlueData software does, or what you'll need to do with Chef and Puppet or some other Ansible type of product is go out and make sure that the IP address and the fully qualified domain name is populated in the appropriate Spark or Hadoop configuration files. Similarly, what you'll want to do is when a container is brought up that has 64 gigabytes worth of memory as opposed to 128 or 256 gigabytes of memory, you will have to tune the configurables within the Spark worker or the Hadoop worker to match that memory or CPU resource that's given to the container. This is what turns the solution from what is essentially infrastructure as a service into software as a service. So rather than just bring up some containers with some software kind of running in it, and then have the data scientist have to tune the software based on the resources that have been associated with the given container cluster, a solution like this will do it all for you so that the container and the collection of containers are all fully optimized and the Spark software running in the container or the Hadoop running in the container is configured appropriately for the given resources for that container. Just to kind of hit this home, what I showed here is just I didn't want to chance a live demo in an audience today, so I took some screenshots, and what I'm showing here is a 4-container cluster running on 2 different physical hosts linked by a common VLAN with using persistent IP addresses. If you were to log into those containers, we support an SSH login, so you can log in using your PAM authentication, Active Directory, all that's fully integrated. So when the container comes up, the only people who can log in are users who have been configured in the appropriate Active Directory group for accessing resources in that tenant. That's all done automatically. Once again, that's where the conversion comes from, infrastructure as a service to software as a service. But what you would see if you just did a quick PS in the containers, if you logged into a container which represented a Spark master node or master role, you would see the master services. And secondly, if you ran into a worker container, it would show only the worker services. And as I said earlier, both of these instances were instantiated from the exact same Dockerfile, and they were modified at creation time, or configured at creation time, I should say. Once again, this is probably too much for a slide, but you can see the slides offline. This is a snapshot of how we recommend configuring storage on the local host for running the container storage. A quick look at performance. I know we're running a little bit long here. So what we wanted to do, we wanted to prove to ourselves that the introduction of a Dockerized environment did not adversely impact the performance of the big data clusters. What we used is the standard TerraSort, the venerable high bench test framework. We used standard data sizes, 100 gig up to 1 terabyte. What we took is we took 10 physical nodes. We installed Spark in the standard native fashion on that Spark, on that cluster of 10 nodes. We ran TerraSort, got the results. Then what we did is we re-imaged those 10 physical hosts, placed the BlueData solution on top, created 10 containers, 1 container per host, and ran the whole thing again. And we wanted to measure if there was any appreciable overhead due to the virtualized environment. And what we found out is that there wasn't. I mean, the performance of the Spark on Docker as opposed to Spark on bare metal was essentially the same. So there was no performance degradation. Just to kind of give an idea about with a solution like this, what you can get is what we were able to do is reproduce the look and feel that a data scientist would want to have. So today, if you install Spark on a bare metal system, a data scientist can, through a URI or URL, access their Zeppelin notebook, and we wanted to have the exact same experience on top of running Docker and containers, and that's what we did through the associating of the instance IP or the network IP with each container and a port mapping solution. We were able to allow with a single click to have the data scientist access their Zeppelin notebook just like they would on a bare metal cluster. Like I said earlier, this can work not only with Spark, but with any big data application. Another shot. This shows where backed it up. Where the data scientist can specify the resources associated with each container. They don't know it's a container. If they looked under the covers, they could figure out, but in fact, it's just a compute node or a computing resource to the data scientist. And in fact, if they want to go ahead and log into the container, they can still do. If they were granted root access to the container, they can go ahead and install new software if that's what they want to do. The look and feel is identical to bare metal. No loss of functionality. So some key takeaways is that even though this is a monolithic application that's not microservices configured, it works fine. It can be deployed well in a Docker containerized environment and gain the Docker benefits of flexibility and agility. ultimately, the whole desire is to reduce cost and reduce the development time and enable DevOps. Requirements, obviously, as we spoke about, is that the Docker image itself must contain, or we believe it contains, all the Spark libraries and ancillary functions. Container orchestrator, while important, is just a component of the overall software as a service experience, and you can tightly control the resources, be it CPU, memory, network, and storage. Data scientist considerations, I've covered this a number of times. Just want to make sure that we maintain all the value props and all the use that the data scientist wants to get, and at the same time addressing the enterprise deployment challenges of the IT organization, where we integrate automatically with Active Directory and LDAP and single sign-on and SSL certificates and Kerberos if you're using that, even in a multi-realm environment, because that's the key. That's the experience that the data scientist wants. It's the key that the IT department wants. They don't want to have to do anything. They want a solution that works right the first time, every time. Okay. And this is just when you're doing it yourself, just be wary. These are the considerations that we learned through hard experience, and that's what we're sharing today with you. So I'll be happy to take a few questions. I know we're at the end of the day, but I appreciate your time, so thank you. Thank you. Sir.
We've experienced some stability issues with Docker. They happen to die. Did you have some observations in this way? And what happens when a container dies, basically, in a stateful application?
Yeah, the question is, there are some potential issues around Docker stability, and then what happens when a container dies? Okay, I agree. We were actually using a pretty hardened older version of Docker, which is not top of trunk, in order to avoid some of the top of trunk issues with that. But ultimately, the case is true. Okay, virtualized environments can fail. Docker containers can fail. Luckily, solutions like Spark and Hadoop are designed for node failure. So what we do is when we deploy the containers of a Spark cluster or a Hadoop cluster, we will run each of the virtual clusters with multiple master nodes, multiple worker nodes, and those containers have anti-affinity policies to make sure they're placed on different physical hosts. So if you lose an entire host, none of the virtual clusters are lost. They will continue to process because the standby master node will pick up and continue to run the solution. Similarly, if you have a problem where a single container crashes on a physical host, it will just be dropped out of service, and the virtual cluster will continue to process with the remaining resources. And we have an API which can be automated, which allow newer containers to be spun up to replace those failed containers. So basically, it's a great question. It's a real-world question. How do you handle failure? Well, you have to be ready for it. There's going to be failures. What you have to do is your system has to be resilient and be able to recover from those failures and keep processing. Good question.
So there was a talk yesterday, and the presenter was telling us that as of Spark 2.3, there is a native support for deploying Docker environments to the worker nodes or the executors. How different is this from that?
Yeah, the question is, and this is a very common question, so what's the difference between what we've talked about here today and you're talking about Apache 2.3, so, and if you listen to the talk this morning, it was kind of brought up as interesting. You can run the Apache scheduler on top of a Kerberos implementation of Spark, and vice versa. You can run Yarn on Kubernetes or Yarn on top of Mesosphere. So what we're talking about is two levels of scheduling. So when the Spark cluster itself is running, so we have a single Spark cluster. whether it's running on a physical environment or a virtual environment, it needs to use a scheduler in order to run its executors, okay? And so that's what we're talking about when we say that Apache Spark 2.3 can launch Docker containers through Kubernetes, through Mesos, through Yarn, okay? That means within the single containerized cluster itself. That assumes that at that time, somehow the original Spark master or the Spark cluster had already been created and instantiated and configured. What I'm talking about here is that first step. So how do you deploy that first Spark master and the first set of workers in an environment so that then it can go ahead and use the Spark technology for spinning up its own executors using whatever container orchestrator it wants. Sorry. Yeah, good question. What's the version policy about Spark? We absolutely do not care. Whatever version you want, we have people running absolute, state-of-the-art stuff, and we have people running old stuff. So any version you want, that the infrastructure and the things I talked about today are not dependent on the version of Spark. Okay. Absolutely. So the question is, can you run two different versions? And that's an ideal use case. So what we often see is people are running Apache 2.1, and they've been running that for some time, and they're comfortable with it running. Now they want to run Apache 2.3. So what they do is they spin up a new virtual cluster running Apache 2.3, and they run it in parallel with their existing Apache 2.1. Once they run the QA and they decide that everything is working as they want, then they'll discard the Apache 2.1 cluster and continue to run the Apache 2.3. It's an interesting mechanism where you avoid runtime upgrades of the solution. You basically spin up a brand new cluster and then at the right time throw the switch and move over to the new cluster. All right, thank you very much. Time.